Thank you for the introduction and the invitation. It's wonderful to be back here in person with Berkeley and catch up with many people who I haven't seen for too long. Yeah, so I'm going to be talking about...
Unless you can be intentional, that ball you cannot move.
Yes, that's fine,
okay.
yes.
Yeah, okay.
That one, thanks, yes. Yeah, so I'm going to be talking about some work that will appear in hopefully 3 different papers, hopefully all before the end of the year. And the aim today is to sort of give the main big ideas and not go into too many of the technical details, but of course I'd be very happy to discuss those with people afterwards and in the future. So let me just say, first of all, a few words about motivation. And something that we know is a very old problem is that we have what looks at first sight to be a perfectly good theory of quantum gravity, at least in regimes where energy densities aren't too high, curvatures aren't too strong, and so forth, which is just treating Einstein theory coupled to matter as an effective field theory. But if we treat that theory just in perturbation theory, which means we start with some self-consistent background, maybe solve the Einstein equations and work in perturbation theory around that background, then we end up with a theory that seems to have too many states in a really dramatic way. So our favorite example of this, which people here know very well, is an old black hole. So you form a black hole from collapse, you let it evaporate for a very, very long time, then the geometry of well, let's see, if we draw a sort of Penrose diagram of the situation, we have some horizon, and if we draw a Cauchy surface, say the singularity up here, if we draw a Cauchy surface, something like this, then the volume of this Cauchy surface grows with time, and in perturbation theory, we seem to be able to put some change some excitations on this slice, and the volume of that slice can become much, much bigger than the area of the horizon in Planck units. So the left-hand side here is the entropy of the sort of the log of the number of states that we can describe here in perturbative gravity, but the right-hand side is the log of the number of states we think we should have non-perturbatively from various lines of argument. And so this looks like a problem. And I guess for a long time, it was thought that what you need is to throw out this perturbative quantum gravity theory, and inside a black hole, some completely different microscopic theory needs to take over, and we need to really understand that microscopic theory. But recently, we've learned that we can get at least a long way by just relaxing this slightly and remaining within effective field theory and gravity, but including non-perturbative effects. So there's at least the possibility that non-perturbative gravity could solve this problem without having to invoke microscopics. And the thing I have in mind in particular is recovering the Page curve from arguments using only gravitational effective field theory. So the aim of today's talk is at least to make some progress towards these developments that suggest that non-perturbative gravity can be helpful here, and give at least get us closer to a Hilbert space interpretation of these things, or a sort of canonical interpretation. A lot of these ideas have been phrased in the language of the path integral. But if we really want to understand the space of states, then that's really a canonical question and something that isn't directly addressed by the path integral. And so we need a different language. So the things that I'm going to talk about have sort of 3 themes which roughly fall into the 3 papers that are to appear. So first of all, we'll talk a little about a non-perturbative inner product on states of quantum gravity. But But when I mean states of quantum gravity, I'm really describing using the same variables we use. I'm not going to pass to some new microscopic variables or mysterious variables. I'm going to use what the most naive, obvious sort of thing you would write down as a state, which is some wave functional that'll depend on a spatial metric and some other fields. So here, this is, if you like, a metric of space. So maybe there's, but the thing that's going to change is not the fundamental fields we're using, but rather the inner product is what we're going to discuss changing. So that will, we have the same underlying vector space to make our Hilbert space, but the Hilbert space itself is different because of the inner product. The second thing we're going to talk about are null states in a simple model. So what I mean here are states like this, where their inner product, when we complete the non-perturbative thing, is actually 0. And if we're going to solve this problem, that there are too many states, but we use the same underlying vector space, well, the only way we can solve that is by saying that some states are actually equivalent to others, or alternatively, that some state is actually really the 0 state secretly. This is, we sort of alluded here to non-perturbative effects, which are effects that sort of scale exponential in 1 over g. These are the non-perturbative effects. But null states like this, these are really sort of doubly non-perturbative in a sense. So they scale like not just e to the 1 over g, but e to the 1 over g. Because these null states will typically involve a superposition over exponentially many terms, each with exponentially small coefficients. So it looks like we've got really no hope of describing it, because it's not something we can just describe with some single instanton. It looks like we really need to sum over all possible non-perturbative effects. I'm just going to describe this in an extremely simple model, something that contains a very simple version of topology change, very down to earth, very calculable. But the thing I think that's exciting and interesting here is that there's actually some emergent effective description that comes out here. And I'll sort of explain what that means. Okay, here it means we're doubly non-perturbative, means we're summing over many geometries, but we don't have to describe things in terms of the sum over geometries. There's some sort of new variables where we can, that are more useful to describe this. Okay, and the third part, which is in the title I gave for the talk, is more interpretation. So I'm going to talk about these non-perturbative modifications you get to the inner product by taking gravitational effective field theory seriously. But I want to interpret these as, in canonical language, as coming from an extension of the gauge symmetries of the theory. And in particular, extending the, so okay, we, in earlier work with Don Marolf, we speculated that, that there was some sort of gauge symmetry at work. We were very vague. We're not the first people to say that. Similar ideas have been advanced by various other people, Daniel Jafferis and others. But here, I'm going to say something very, very concrete, where we're going to extend the diffeomorphism symmetries to include some diffeomorphisms that are discontinuous. And that will be the final part of the talk. But perhaps the thing I'm going to emphasize before we start is that the fact that we're using these gravitational variables means that I'm going to keep geometry and using geometrical language the whole time, and I'm not going to, I'm not going to sort of be using any notion of duality, ADS-CFT, that has some different and new set of variables. I'm not going to make any speculations about what might be going on microscopically. We're going to really take geometry seriously and just see how far it can take us. Okay, so with that, let's start with part 1. One is computing inner product in gravity. Okay, so as we've said before, the states we're going to think of as being some wave functionals of fields that live on a spatial metric and maybe whatever other fields, matter fields that might be around. So these are our states. And if we've got two such wave functions, the question is, first of all, using the language of the path integral, how should we compute the inner product of our states? So this we can think of, we've got some complete space-time, M, and we choose some particular Cauchy surface, sigma, and G here is the induced metric on this Cauchy surface. And of course, we've got to deal with the fact that there are many different ways to slice this, impose constraints, and these sorts of things. And those constraints will be playing a key part throughout the whole thing. But okay, that's the idea. So how do we, if we've got two of these states, how should we compute the inner product? Well, we have, here's what I'm going to suggest is the right way to do it, is you have sigma primed. This is where some particular state, our second state, psi primed, is defined. Okay, so what we want to do is compute the inner product between a state psi prime and a state psi. And this has some wave functional of a metric G restricted to sigma primed and other fields. Maybe I'll just suppress the other fields for now. And we've got some other Cauchy surface, sigma, down here, and that's where this first state, psi, is defined. So that has some induced metric G. And we're going to imagine these bound some space-time. So there's some space-time manifold M that's bounded by sigma and sigma primed. And at least in principle, we should compute the inner product by integrating over all metrics and the matter fields on this M. And again, perhaps I'll just suppress matter fields, but you can assume they're there all along. There's some action, it's a Lorentzian path integral, and it's weighted by these wave functions. So psi of G restricted to the surface sigma, psi of G restricted to the surface sigma primed. These are the boundaries, and I've already put a bar here. It's the complex conjugate. Okay, or more generally, if there are some other fields, this might be a CPT conjugate operation, but for simplicity, we'll say CPT trivially, and it's just complex conjugation. Okay, and I'll just give a sort of example for if this looks unfamiliar to suggest that this is something that's at least reasonable to do. So I'm going to take an extremely simple example, which is one-dimensional gravity, where this integral over all possible metrics bounding two Cauchy surfaces is very simple. The only metric variable that's left over in one dimension is just the proper length, proper time, I should say, between the two boundaries. So this integral over metrics is really just an integral over some proper time. And now these wave functionals here, there's really no metric variables, there's only matter variables. So there's some state in a matter theory, psi primed and psi in some matter theory. Okay, maybe an example of a one-dimensional gravity here might be a mini superspace model where we say we've got a cosmology with some symmetries and so forth and effectively reduce that to one dimension. And the path integral of matter fields on this one-dimensional geometry is, well, you put the matter fields on some segment of some finite time t, and all that does is compute the time evolution operator on that segment. And then we're going to integrate over all spacetimes, and I'm going to integrate, in fact, this sort of time, this lapse, will integrate over the whole real line. So we're going to include both possible time orientations. And the result you get from doing this is that this integral over t, at least in a distributional sense, you can define this in a sensible way, and it just imposes a delta of h. And if we were going to canonically quantize this theory, we would usually say, well, we should take into account diffeomorphisms by imposing constraints What are the constraints? Well, in this case, it's just h is equal to 0, Hamiltonian constraint. This is what you get from treating the time evolution as a gauge symmetry, and this delta of h precisely just imposes that Hamiltonian constraint in a strong way and says that the only part of the matter fields that matter are the zero energy piece, the piece that solves the constraints. So, okay, this at least at first sight looks like it's something reasonable. So we're going to run with this, unless there are questions. Okay, good. So everyone's happy with this. I'll maybe just make a few comments that are not going to be useful now, but we'll remind you of them again when we get to part 3, which is that, well, okay, one comment that will be useful is that this inner product, once you've imposed delta of h, or done this path integral, is no longer necessarily a local functional of these metrics and other fields. The reason being that, for example, you could pick these two states to be two different time slices in effectively the same metric and the same space-time, and when you constrain to some Cauchy surface, they may look very different, but really they just describe the same state in two different gauges. So in that case, this inner product may not look local. So the fact that things that appear later are non-local is not as radical as you might think. The second point I'm going to make is to just, in this one-dimensional example, recognize as e to the minus iht. This is really a gauge transformation. In this example, we're just gauging time translations. So this is a time translation operator. And so the path integral, it naturally imposes the constraints by integrating over all possible gauge transformations. And the final comment here is relating to these null states, is that I could take two different matter states here, two different states psi of the matter fields, which are the states sort of before imposing constraints. And as long as these states agree, have the same wave function on the zero energy piece, they can differ for different energies. So they can be different states, but they're physically equivalent. So that means that these two states are two different representations of the same state. We could say they're gauge transformations of one another. And null states appear as the difference of two gauge equivalent representations of the same state. So the natural way null states can appear in this picture is to say differences of gauge equivalent representations of the same state. Okay. So far I just talked about this. This sort of delta of h is really imposing what you might think of as perturbative constraints, or constraints that can be built up by exponentiating some infinitesimal generator. The thing that's going to be most interesting to us is things that can't be built up by perturbation theory, things you can only see really by doing something non-perturbative. So that, in this example, this space-time we could be built up by adding little chunks of smaller space-times together, but if we have something more interesting, so in particular we'll be interested in space-times that include topology change, that's not true anymore. And so the real thing we're going to be interested in are not these perturbative things, exponentials of small diffs, but rather large diffeomorphisms, things that can't be exponentiated from small things. Okay. Okay, so the way these so it'll be a helpful notation because we're going to be talking about sort of two different types of inner product here. To use a different notation just to know exactly what we're talking about as we go along. So I'm going to use these double line notations to denote the full physical inner product, the full sort of non-perturbative inner product. So this is some non-perturbative inner product. And we'd like to build that from a single line inner product, which I'll just denote like this. And this inner product here is, think of this as the inner product you get in perturbation theory. So we'll imagine that we've already done this sort of thing to impose the constraints under infinitesimal diffs, and the only thing we want to have to deal with are these non-perturbative things. So this inner product supposes we've done with the infinitesimal ones, but we want to include some non-perturbative stuff. And we're going to insert some matrix of inner products here. And the way we're going to compute this matrix of inner products eta is by some sum over manifolds of different topologies. So there's going to be some sum over manifolds, and each manifold is going to contribute some eta m to this inner product. So eta m, there's first of all an identity piece, so that takes into account the sort of trivial topologies, the stuff we already dealt with. And then there's going to be some other stuff. And term by term in here, in typical situations where we're talking about physics in this room, in the solar system, and that LIGO sees and so forth, these terms here are going to be exponentially small. So really, we can throw them out. We shouldn't have to worry about them, which leaves physics in this room safe. But the important thing is there are going to be many of these terms, or sometimes we're going to do a very delicate experiment that involves summing over many things where these terms are going to come in and be important. So for these sorts of questions we asked about in the motivation, those things will be important. Okay. So maybe we'll just, in one dimension, we can give an example of the sorts of sums we're going to have here, which is to imagine that we're not just talking about the states of a single universe, which is a zero-dimensional space, but we actually have two universes. And there, when we integrate over all manifolds, so here's our state psi prime, and here's our state psi, that's a wave function here on 2 points for psi, a wave function on 2 points for psi primed. There's nothing in particular that says we have to identify the point on the left with the point on the right. So we could also include a term that, okay, maybe it's a bit much to call it topology change, but at least it's a sum over different topologies where we identify things in a different way. So here, eta is equal to 1, or the identity, plus pi, where pi is a permutation, the guy that swaps the two copies. And actually, this is really a conventional part of diffeomorphisms. This is like a part of the momentum constraint, if you like. So the momentum constraint tells me that I shouldn't care about the coordinates on my spatial manifolds. Here, the coordinates is just an ordering of the 2 points. One is 1 and one is 2. Okay, a simple version of coordinates. It tells us that I should actually care about the gauge equivalent metrics. So in particular, there's a diffeomorphism of space that swaps the two universes, and I should gauge that diffeomorphism. So this pi is appearing as that gauge transformation. Okay, but we're not here to talk about boring things like swapping universes around. Well, okay, we kind of are actually, but we want to talk about something that's a little more interesting. And that is a replica wormhole. So this part will, to some extent, assume a little bit of familiarity with what a replica wormhole is already. For those of you who aren't in with the nitty-gritty of these things, I'll slightly apologize for going over some of the details very quickly. But okay, we won't be relying on them on very essentially later on. So, okay, so the idea of a replica wormhole here is we have this eta m, so one of these terms in our inner product. One of the contributions to this path integral over all geometries computing an inner product. Okay, and this is going to be an operator that's a little bit like what we had with the permutation earlier. First of all, it's going to come with a coefficient, which is e to the minus a over 4g, which is a familiar, although, okay, there's a, okay, so this is going to be our new operator eta m that is an inner product induced by a replica wormhole. So, okay, so the first point here is to say that because of this coefficient, this eta m is exponentially small. Okay, so it satisfies this thing. We shouldn't worry about it too often, as long as this area that's appearing is large in Planck units. But now I should tell you what is this operator here. So it's labeled by two things. So it's labeled by pi, which is a permutation, so it is kind of. And it's labeled by I, which is contained in sigma, or rather sigma primed here. So that just means that this is some region of space. Okay. So this is, okay, I should tell you what this index n is, first of all. So these permutation operators, they make sense when the Cauchy surface we're interested in, computing in a product, is equal to or at least contains some copies of identical Cauchy surfaces, sigma 0. There's some disjoint union of these, so there are n of these guys. These are things that appear in the calculations of Renyi entropies, for example, for if you want to compute the entropy of some radiation that comes out from a black hole or something like this. Use the replica trick. That means you make copies of your system, and these guys are the n copies of the system, the n replicas, they're called. Okay, so here is our sigma 0. So I've drawn here an n equals to 2 example on the right-hand side, n equals 2. So this at the top, make sure I got this right. Yeah, so the top is the first replica, the first copy, and the bottom is the second replica. Oops. And if we didn't have this permutation operator, then when we take the inner product, okay, so the left line and the, have I got this right? I've got my labeling wrong, sorry. Okay, so this is the first replica, and this is the second replica. And this piece down here is where we insert our wave function. So in fact, down here, we have a wave function psi, which describes the state on these two initial Cauchy surfaces. So these are some manifolds that interpolate here. And along here, we have the second state, sigma primed. So what we're trying to compute is some matrix element. Oops, I should say. Okay, so we put wave functions psi as boundary conditions here, wave functions for psi primed as boundary conditions here, and if we didn't insert this funny pi operator, the sort of obvious thing to do would be we do the path integral as before, where we evolve to some future slice sigma primed, and now we're identifying the fields on this future slice sigma primed. So this is a little bit like the time evolution we had before, but now there's a little bit of forward time evolution, which is weighted by e to the plus I times the action, and there's a bit of backwards time evolution, weighted by e to the minus I times the action. Okay, so without this swap operator, this is just a time evolution forward, identify fields, and a time evolution back. So it's like okay. So this, think of the path integral on the bottom part of the board as computing the matrix elements of u of t, a time evolution operator, and the top of the board is u dagger of t, the conjugate time evolution operator. And if we just identify fields in the obvious way, which means inserting the identity, then we get u dagger u, which cancels and we can ignore it. But what we're going to do instead is identify fields in a funny way, which means how the colors say. So in the blue region and the green region, we do the obvious thing. Nothing interesting is going on. But in the red region and the yellow region, we swap the fields on the two copies. So for example, maybe we've got a field which has some configuration and takes some particular value over here. The boundary condition tells me that it should take the same value over here. So it's permuted. Okay, so that's what this permutation operator, pi hat of I, does. And I should say what I is. I is this region. So it's a spatial region on sigma primed. Okay. All right, so if we inserted this, if this region I was part of the original space sigma, it's just permuting the field in some region, but we might want to insert it on some other slice, and then we think of it as like a Heisenberg operator, like U dagger permutation U. Evolve, permute, and evolve back.
The condition that you can do this smoothly is extremization. Because you need.
Yes. So, okay, so you might object here that these don't give us smooth Lorentzian manifolds because there's something funny going on at these points here. And okay, here I don't want to go into all the details, but perhaps the main thing to say is that the Einstein-Hilbert action actually, whatever it is, 1 over 16 pi g, can be assigned some finite value for these sorts of spacetimes. So, for example, you can do an infinitesimal deformation that makes these spacetimes slightly complex, just some I epsilon. In fact, it really is the same as the I epsilon you're familiar with, that renders this action computable and finite, and it gives you a contribution in Lorentzian signature that goes like I times the area of the boundary of the island in 4G. So that's where this factor here comes from. Yeah, okay. There are several ways to compute this, and these are all, okay, these give sensible results. This is old stuff going back into the 90s, Luco and Sorkin, if not before. We're just sort of reusing that. So, okay, at least a reasonable reason to include these have finite action, and my idea is I'd like to integrate over all such things. Okay. And yes, this is related. If you want to actually look for a classical solution, then that's where the quantum extremal surface condition comes from. But in this kind of context, inevitably that'll involve complex metrics and other such complicated things. But for us, it won't be very important to have a saddle point. It's just that they're there as configurations in the path integral. Okay, yeah, so hopefully the generalization is clear here. N is the number of replicas, the number of copies of the system, or the number of identical pieces. Perhaps these could be sort of distant pieces of the same system. Pi is a permutation that acts to move around these different systems, and I is the region on which we're performing this permutation. We could even label, okay, you can imagine various generalizations for yourself. Okay. And okay, and this permutation operator is the matrix elements of this permutation operator are computed by the path integral of the matter fields on this geometry, and this is really at least a Lorentzian version of geometries you may be familiar with for computing entropies in quantum field theory using the replica trick. It's really exactly the same thing. The only difference here is that the metric is dynamical and we're summing over metrics. Okay. Questions? That was perhaps confusing.
Is there any reason you can't do this in a single space, like switching?
No. No, yeah, so this is why I didn't want to get into trying to imagine generalizations to yourself. This is, if I have two identical copies of exactly the same system, then, okay, this is something I can do, but of course you can imagine generalizations where I do this with different pieces of the same system or all sorts of other things, yes. And those will certainly be there. Okay, so that means, so now we've got these contributions. So the full matrix of inner products will, okay, maybe there's some other pieces, but at least will include, okay, there's the identity piece, which is the boring perturbative piece, plus there's some sum over all possible permutations, except the identity, because that's boring. And if you like, an integral over all possible islands of these guys. I haven't explained what this number mod pi is. It'll come up later. It's not so important right now. Okay. So one point of comment is in order, which is to say that this kind of modification to the inner product clearly breaks some notion of locality. In a very precise sense, this breaks cluster decomposition. It means that the inner products of states of very widely separated systems have some contribution that doesn't decay with the distance between them. And this looks very bad for locality. There is a story that is important, but is not the part of the story I want to emphasize here, which is to say that, which is to do with the fact that there are super selection sectors in which you do restore cluster decomposition. So this is related to the old sort of story due to Coleman and Giddings and Strominger of alpha states and baby universes and so forth. I'd be very happy to talk for hours about that, but I don't want to talk about it today. The point today is to emphasize the geometric origin of these sorts of modifications to inner products. Okay, so that's part one. Maybe I'll just briefly make the comment that these sorts of things, one reason to believe in them is they're extremely useful for example, computing the entropy of radiation that comes from a black hole. There's a detailed calculation that gives results that agree with expectations from completely disconnected points of view. So we like these geometries, we want to take them seriously, and we want to see how far they take us. Okay, so for the second part, I'm going to sketch a very simple model of this, where we're not going to do something so complicated as this. We're going to abstract to the simplest version that we can solve and say lots of things about. Okay, so the idea here is that we have some black hole that forms from some collapsing star, and we let it evaporate. Some Hawking radiation comes out. It's entangled with some Hawking partners inside the black hole. This is the semi-classical picture you get of evaporation, with a very small assumption that whatever goes on at the very end of evaporation, where Planckian physics becomes important, well, what happens is the black hole evaporates completely, so we're left with empty space containing some radiation and this interior piece. And we're going to play this game above, but we're going to have a very simple version of the island, which is, will allow, sorry, yeah, this I is the region that people call the island. I think I probably didn't say that before. But, we're going to say the island, or this region that we're permuting, just consists of the entire black hole interior. So one way to think about this is that when we compute the inner product, we imagine letting the black hole evaporate completely. What are we left with at the end of evaporation? Well, there's some empty flat space that has some radiation that's streaming away from now an empty point, which is just where the black hole once was. But we're left over with some closed universe over here, and the closed universe is this I. It's what once was the black hole interior. It's got something funny going on over here, right in this corner, where there's some Planckian nonsense that we don't know much about. But at least it's reasonable to say that these islands, we should treat them like closed universes. We should have some, in particular, if we've got two of these guys, we should think of the wave functions of two of them as symmetric. In particular, one way of saying it is there's a diffeomorphism symmetry, a spatial diffeomorphism that permutes the two copies, and we should gauge that diffeomorphism. So that's what we're going to do. We're going to compute the inner product here by, okay, so we have this inner product, psi primed 1. If we have n of these black holes, psi primed n, psi 1, psi n. And so these are supposed to be states on some earlier time slice, sigma. So this is a time slice that maybe enters the black hole at some time t. And to compute this inner product, we first evolve to this final slice over here, the blue slice, sigma primed, which is the interior union the exterior. Okay, the colors are good. Sigma primed. And then we take the normal inner product on the exterior, and we symmetrize on the interior. Okay, that's the game. And this evolution to sigma prime is very important because when we do that evolution, we create some Hawking radiation, some entangled pairs of quanta on the inside of the black hole that will end up getting swapped, and some quanta on the outside of the black hole that won't end up getting swapped. And perhaps I won't go through the exercise of computing what this does. But if we say that there are, on this interior at this time, there's a q-dimensional space of possible modes. Sorry, there's a p-dimensional space of possible modes on the interior. So that means that these psi's are in some p-dimensional space. And the late radiation, okay, yeah, so let's see, what we want to say is that our states are in some p-dimensional Hilbert space. The late radiation is going to create states in a q-dimensional Hilbert space. So that means there's some p-dimensional space of early modes, a q-dimensional space of late modes, and that q-dimensional space of late modes is purified by a q-dimensional space of possible radiation modes. So this is the late stuff we trace over. And what we find is that this eta, this matrix of inner products, is just a sum over permutations. And I'm making a slight simplification here, but it gets weighted by this, the number of modes that are yet to escape. And I guess there's an n minus length of pi. And then there's just a permutation operator. Okay, so that means that we don't just symmetrize these wave functions, summing over all the possible permutations of the indices that live here, but we do a weighted symmetrization, where the different permutations are weighted by this factor. And now I should tell you what pi, this length is. Well, okay, maybe I'll say what n minus pi is. This is the number of cycles in pi. So we write each permutation as a product of disjoint cycles. We count how many cycles there are, and this pi appears. And actually, the same thing shows up in gravity in a topological context. It's related to the Euler characteristic of these manifolds we had up here. This is a little bit hard to see, so maybe I'll just quickly draw a diagram to explain where it comes from. So we're feeding in some, okay, so eta is some operator that acts on n copies of the Hilbert space. So we feed in n states, so maybe 3 states, let's say. And then we're going to have n states at the end that we're going to contract with these psi-primed indices. So it's some matrix. These are the n ket legs and the n bra legs, all the way around, if you like. And the first thing we have to do is create some Hawking radiation. So Hawking radiation is like a maximally entangled state, at least in some approximation. It's some entangled state. And one of the legs of this Hawking radiation we feed in to the interior of the black hole. So this is what we call the island. And this other leg is the exterior. So we do the same over here. Now the exterior, we do nothing to it, we just contract it, we trace it out. That means we're taking the ordinary inner product. And we do the same on all the copies. So this is just not contracting. And then over here, we do a permutation. And we sum over pi. So maybe we'll do a simple example here, which is we take all these external legs. So these get contracted in the ordinary way, these get contracted in the ordinary way. But now what we're going to do is permute these. So these 2 legs are going to swap, and these 2 are going to swap. So this is the permutation. And maybe I should have used different colors here, sorry. Okay, if we follow what happens to this extra radiation we added, it ends up in a closed loop like this, right? So that when we take all the possible states that can run in this closed loop, we get a factor of q. If we hadn't swapped, we would have got 2 loops. We would have got a factor of q squared. Right? And okay, so we sum over all the permutations, and there's also a factor of 1 over q to the n. So the unswapped version, here n equals 2, these q squared, the 2 loops, they get cancelled. So the unpermuted thing just appears with no coefficient out here, a 1. But the permutation means we get fewer loops, which means we get a suppression by factors of q. And these are these factors of q. And so this number, this mod pi, is just counting how many loops you've lost by this contraction. Okay, so this is an extremely simple model. It's a concrete inner product. So here's a matrix. You can study this as a matrix of inner products and see what happens. And in particular, what we were interested in was the dimension of the physical Hilbert space. So how many of these states really give you different states, or they have different inner products with everything else. So that's really asking what's the rank of this matrix eta. Okay. And I'll just very briefly sketch how you can calculate this. And, well, maybe I'll first of all tell you the answer. So if we take at least the log of the rank of eta, so this log of the rank of eta is like an entropy. It's the log of a dimension of a Hilbert space. And the 1 over n is there because we're taking the inner product on n black holes. So this whole thing, the whole thing here is the entropy per black hole. Okay. So this is really counting states of a black hole in an honest way. I've got an inner product, includes some modifications from topology, but I want to compute how many states there are, not in some indirect way, but really by looking at by diagonalizing the inner product and checking how many independent rows it has. And if we take large n, then what we get is something you might call a page curve. It's a minimum of 2 terms. If q is small, that means the black hole, if q is very large, it means the black hole is sort of young, then it's exactly the number of states you would have thought. You haven't thrown away any states at all by this junk. It's the same as the identity matrix. You just get p to the n states. But if the black hole is old, suddenly this eta starts picking up a load of null states. There are lots of things that we have to throw away, and the number you're left with is log q, and this in this model is analogous to the Bekenstein-Hawking entropy, area over 4G, in this context. In fact, it's parametrically, if you really use this model for a Schwarzschild black hole or something, it is A over 4G up to some number of order 1, about 1.8 or something. Okay, so we really get a page curve. And the way this calculation works is, because we're using all the permutations, it's natural to decompose this Hilbert space, which is c to the p. So we've got, it's the n-fold tensor product of c to the p. So this is a c to the p, this is a c to the p. So that's the space on which eta acts. And to decompose this into representations of the symmetric group. And there's this Cherval duality story that some of you will be familiar with, some of you won't, that this space decomposes into representations of the symmetric group times representations of the SUPs. So SUP is just the thing that acts by unitaries on each block separately. And sim-n is the symmetric group that swaps these guys around. And So the full dimension of this thing, you can ask to act as the sum of the dimensions on each of these representations. And what these do is actually throw away some of the representations. So what we have to do when we take the physical Hilbert space, we replace this thing with the full physical Hilbert space on n copies, is we actually say that the number of rows, okay, people will remember that the dimensions of the symmetric group or SUN are labeled by Young diagrams. You have n boxes, and these tell you about how to symmetrize and anti-symmetrize over all the indices. And okay, I'm going a little bit fast here, maybe. Okay, so the physical Hilbert space means that we throw away, that means we throw out the kernel of eta, the stuff that eta kills.
Sorry, can you remind me what's actually P and Q?
Sorry. Yeah, so P, if you like, is so we split up the interior into two pieces. We're interested in some slice that contains only a part of the interior, and this has a p-dimensional Hilbert space. So P, if you like, maybe you can think of it as 2 to the number of early modes. It's the exponential of the, or it roughly grows exponentially with the age of the black hole.
Okay, talking about Hawking modes.
Hawking mode, yeah, sorry. So it's 2 to the, yeah. You get a factor of 2. If you've got some number of modes in here that can be either up or down, each mode gives you a factor of 2.
Yeah,
or a factor of 2. I'm talking about the interior Hawking modes. Yeah. Yeah.
Not
So
necessary excitation on top of it or some semi-classical excitation. It's just, this is a model Hawking.
this is just, yeah, this can just include the Hawking modes. I mean, it could include other matter you threw in, all sorts of other things. But well, for now, we'll say it's just the Hawking modes. And the Q here, similarly, is the dimension of the Hawking interior modes that to be emitted in the future. Okay. Hopefully we're following. Yeah, and okay, the number of Hawking modes to be emitted in the future is equal to the exponential of the entropy of the Hawking modes to be emitted in the future, which up to an order 1 factor is the same as the black hole entropy. So that's Q is really e to the a over 4g up to some order 1 fudge factor, which is, okay, this is not supposed to be a perfect model. To fix the order 1 fudge factor, you have to use islands. Maybe I should actually say this model is not new. It's appeared in various different forms. So it was a paper of Polchinski and Strominger in 1994, I think, described this, going a long way back. But also, it's not supposed to be obvious, but in this West Coast model of JT gravity with end-of-the-world brains, if you fix the spectrum of energies and talk about the space of end-of-the-world brain states, so P there is equal to what they call K, the number of different end-of-the-world brain states, and Q is roughly e to the S0, which is their entropy parameter in JT.
Wasn't that the other way around?
No, this is P is like the number of early. So this P here in their model, it gets replaced by an end-of-the-world brain with some index. Okay, so maybe I should have said this to begin with, because this is a useful thing to anchor on if you're more familiar with that. Okay, so yeah, if you want to talk about the rank of the inner product on the end of the world brain states or that West Coast model, it works precisely the same. All the other funky stuff with their geometry, it's the same geometry as well. The stuff that they have with adding handles and so forth just changes the energy spectrum. But if you're just interested in the end of the world brain states, it's really literally the same model. Okay, these factors are slightly different, but it's okay. Morally, it's the same model. Okay. Yeah, I should. Yeah, okay, so I won't say very much about this at all. Okay, apart from to say the way you compute this kernel, the dimension of this Hilbert space, is you decompose all the states into representations of the permutation group. And now, if you, the representations are labeled by whether you get signs, when you anti-symmetrize things, people will recall that this Young diagram corresponds to the symmetric representation, which means you don't, or the trivial representation, which means you don't do any, hang on. Okay, it depends on which representation I'm talking about. I want to talk about representations of SUP here. So this is talking about the symmetric representation, means symmetric tensors, swap indices, wave functions where swapping indices don't do anything. These guys correspond to anti-symmetric wave functions. And these guys correspond to something in between, where you do some symmetrizations and some anti-symmetrizations. And the point here is, these Q labels, is that if you try to anti-symmetrize over more than Q indices, you run out of indices. So that means that when the Young diagram gets to grow more than height Q, more than Q rows, you try to anti-symmetrize over Q plus 1 or Q plus 2 different indices, but there are only Q indices to choose from in this radiation you traced out, so you kill the state. So that means that we only have Young diagrams with rows less than or equal to Q. So that's put some constraint on our Young diagrams. But now we can ask about the dimension of the spaces associated to different Young diagrams. And it turns out that you do is you rotate a Young diagram. So a Young diagram after 45-degree rotation looks like this. And the dimension of a space corresponding to a particular lambda is described by an effective action of a sort of Fermi sea that lives at the edge of the Young diagrams. So you can literally write this thing, the dimension, as the exponential of minus some action, where this action is the energy of some fermions with a log potential, with a sort of Coulomb gas of fermions. So what you get from this description is you have many, many, many copies of your system. There's some complicated space of topology change that you think you've got no hope of describing it, but you pass to this other system a bunch of fermions that interact with this Coulomb sort of potential, this log potential, and it turns out that that is dominated by a particular shape of Young diagram, and if you put a constraint that there's some maximum number of rows, that constrains the Young diagrams you can have, and okay, you do the calculations in detail and you get this result. And I'd be happy to explain the details afterwards.
Exactly replica you're doing, right?
It's exactly the replica. Yeah. This is really the same. Yeah, the thing that's different in the replica trick is that one of these terms dominates.
Yes, and also replica after evaporation, you can swap. Maybe island is kind of disconnected from space.
That sounds right. The island becomes just a closed universe.
Yeah, but it's
and you should symmetrize over the island at that point, yeah. So I should wrap up. I did promise to say words about gauge symmetries. Fortunately, I already said most of them. So part 3 will happily serve as a summary. I decide exactly what I want to say. Okay, so in this simple model over here, we wrote this eta. It's a matrix of inner products. We wrote it as a sum over some permutations. Okay, so in the path integral, these permutations label different topologies that appear. So this is the sum over topologies. But we also use this language where we said, once the black holes have evaporated, we have these closed universes. We have diffeomorphisms that permute those universes. So this I can really think of as being a sum over elements in some group. And this group has some representation. So this eta is summing over representations of a group, and you can also think of this as being proportional to the projection onto the space of G invariant states of the group. So it's really like that delta of H we had earlier. In fact, the delta of H we had earlier, you replace this by an integral, you replace the group by e to the minus IHT, it's the same thing. You can think of these as being, these topology changes as inducing some gauge transformations. The case of the islands, that was a little bit funny because we had some coefficients, e to the minus area coefficients out here. And we should also ask, what is the gauge symmetry? So for the case of the islands, the gauge symmetry in question there is really, it's just like this example where we have the diffeomorphisms of different closed universes, spatial diffeomorphisms. They're still diffeomorphisms of space, but they're funny because they're discontinuous diffeomorphisms. Okay, I know the discontinuous diffeomorphism is a misnomer, okay, it's a self-contradictory name, but I hope you understand the point, is they're discontinuous maps between manifolds that we integrate over. This is, I find this very attractive because this is a sort of bottom-up picture that leads to this idea that space-time is emergent. So people like this idea that there's no space-time in the fundamental degrees of freedom, there's just sort of a bunch of qubits in some abstract sense, there's some Hilbert space, or maybe the Hilbert space of a CFT. And then at some low energies in the right sort of states, we can describe geometry as some emergent thing. And maybe the shape of that geometry is encoded in the pattern of entanglement of those bits. Here we're not starting with a bunch of bits and getting geometry. We're starting with geometry and starting to creep up on this idea that it's starting to fall apart in some circumstances. The idea that some piece of space over here neighbors another piece next door is something that's really state dependent, and there's some kind of gauge symmetry that really swaps these things all around. And that's where these coefficients come in. They're a curse, first of all. They don't look like they fit into this formalism. You shouldn't have room for coefficients. But we saw some coefficients up here as well. And the way these coefficients appeared was by tracing out or integrating out some degrees of freedom. In this case, it was the late Hawking modes. The idea in the islands is that these same coefficients, e to the minus a over 4g, come from tracing out some short distance entangled modes that live near the entangling surface. Where these modes come from is a mysterious question, perhaps for a microscopic theory to answer, or a string theory or something else. But at least that gives an explanation for where these come from, tracing out some modes that you haven't included in your theory. And they also tell you that the suppression of these diffeomorphisms is only due to the entangled nature of these states. So the fact that this point of space is very near to this point of space is because there's some short distance stuff that's highly entangled and preventing this sort of diffeomorphism to be important, and that's holding space-time together. And okay, that sounds maybe radical, but we really got there by taking a very conservative approach, starting from just an effective theory of gravity and including some mild topology change. And I think and I hope there's probably a lot more to be learned from this approach, and I invite your questions afterwards, and thanks for your attention. Yes. I have no idea why you thought that was a simple question. Yes. Yeah. I'll briefly say something about it, but we can talk in more detail later. Yeah. So this idea of imposing gauge symmetries by having a physical inner product is equal to some inner product. You have sometimes what's called a kinematic space. That's a sort of bigger Hilbert space where you haven't imposed the constraints. and then you have some eta that projects onto the constraints, and you want to sort of construct this kind of eta. That's sort of the basic idea of refined algebraic quantization. And in particular, there's a version of that, a sort of subclass of refined algebraic quantization, where eta is the integral over the group of gauge transformations. And okay, there's lots of technical things we could say here, and the relation to BRST and all these other things, but yes, it's some of the underlying ideas are definitely similar. Yeah. Maybe I should the last thing I should say is that the thing I really want to take seriously here is that this approach is not what we normally do in gauge theory. I could explain why afterwards. I'd be happy to. Normally we introduce some ghosts and we impose BRST constraints to some level of the ghosts. This refined algebraic quantization is like working at the top of the highest possible ghost number, which is not what we typically do. Normally we work above a ground state where the ghosts annihilate some constraints, like positively moded ghosts annihilate our vacuum and negatively moded ghosts don't. And I'm probably saying more than I need to. But okay, for the infinitesimal diffeomorphisms, this is not the standard thing to do. The thing I really want to take seriously out of this is how it deals with the sort of non-perturbative diffeomorphisms. These topology changes that can't be got by exponentiating things, and group averaging is a nice language to talk about that. That part. Sorry?
Unoriented string theory.
Well, yeah, so if you really have discrete gauge symmetries, this is sort of the only way to go, as far as I know. I mean, maybe not, but yes. Sorry, it was a question at the back? No?
I have a question.
Sure.
I sort of asked you this morning already, but this picture that you have at the end about entanglement holding together geometry, feels like the rest of the talk was special to black holes, but it seems like here at the end you're trying to say this is a more general property of space-time. Do you think that this property at the end is really more general than black holes?
Yes, I think so. Yeah, so the thing that's special about black holes is that, okay, so what I was saying here is that if you have a very smooth state, so maybe if you look at the state below scales of a TV or something, it looks beautifully smooth, and then you're guaranteed to have vacuum state of entangled modes all the way up from TV to a Planck scale, and that sort of suppresses all the effects that you'd see from this fact. It's just glued together too strongly. The thing that's special about black holes is that you can have extensive effects that overcome the short distance microscopic effects. So here, the area, the thing that competes with the area in Planck units is the extensive amounts of radiation that comes out of a black hole, which means you have to wait for a long time and so forth. And so that can start competing. So, and maybe there are other circumstances where you can have the same competition. Sort of, okay, speculatively you might say de Sitter space in late times, and but concretely I don't know of other situations where this is important. Yeah, you need to sort of violate an entropy bound. You need to have, in some sense, a state with more entropy in a volume than the area of the region in Planck units, which is obviously doesn't happen in everyday life very often.
Just want to follow up on the question. So are the replicas here important in your story? Like, because in the examples you gave about black hole, so because in the black hole story we know we need replica to compute the ring entropy.
Yeah.
Here, how do you think of this?
Yeah, so I made these sort of comments about superselection sectors and alpha states, and I wanted to try to de-emphasize these because I don't think it's very special to replicas, but it's certainly true that all the simple examples I talked about sort of involve these replicas and alpha states and so forth in some way. My thought is that actually if you wanted to get rid of the replicas being important, to actually restore sort of factorization and sort of cluster decomposition, the way to go is not to get rid of these sorts of effects, but to ramp them up, is to make is to make more gauge symmetries so that the non-factorizing states become null. It can be, or so that most of the alpha states become null states. But I think that's extremely speculative. Yeah, so I might hope that some microscopic effects in string theory or something, if you're interested in n=4 super Yang-Mills and factorization in that kind of string theory thing where we don't expect to have these effects, perhaps there's something about the microscopics, brains and whatever else, that makes the null states so strong that they kill all the alpha states and restore factorization, which is sort of, okay, it's kind of surprising, but.
One more question. So this Berkeley Center calculation on this Young diagram, is the point that with this technique you can compute this log rank normalized by n exactly?
Yes, yeah, so what you can do, well, okay, it's not exactly. Well, you can, the place this sort of Fermi C picture emerges or becomes useful is in a limit where the number of copies is much, much bigger than 1, and P and Q are both much, much bigger than 1, but you fix the ratios n over P squared and n over Q squared. And then you can describe them in, then it becomes a saddle point of this Fermi C. So the dimension becomes e to the n times the action of some saddle point with some power law corrections.
So what I mean is you get this formula, like this item formula, but does this give you like correction terms to it?
Yeah, so this formula is really talking about what happens when n is the biggest parameter in the game. Then you approach this and you can calculate that explicitly. There's lots of details that happen when these two things are of order 1. And then you can have all sorts of different shapes of Young diagrams. This is something that's, okay, versions of this has been studied in the mathematics literature I should cite the inspiration, get the names right. So yeah, stuff like this. If you just do the version of this where you talk about the squares of the dimensions of the symmetric group, that's what's called the Plancherel measure on the symmetric group, or representations of the symmetric group. And this stuff there was worked out, not quite in this fermion language, but was worked out, all these details, by Logan and Shep in the 70s and by Vershik and Kerov in the 80s. So, and it's been generalized in various places in mathematics literature since. This is really just picking up tools that were lying around. And yeah, the same thing might be familiar to some people from gauge theories, like QCD2. This was like Douglas and Kazakov in the 90s had some stuff about in two-dimensional QCD, for example, that there's a similar kind of dynamics of Young tableaus that describes phase transitions in that theory and so forth. So it shows up all over the place.